Okay, let's start. Welcome to New England Dynamics and Number Theory seminar. Today we have Juno Seong, who is from California, and the title is right here: Avoidance Principle and Margulis Functions for Expanding Translates of Unipotent Orbits. Thank you.
Thank you. Hello, I am Juno Seong, a PhD student at UC San Diego. And today I'm going to talk a little about my recent result with Anthony about avoidance principle and Margulis functions for expanding translates of unipotent orbits. So to begin with some historical notes, so avoidance principle is the problem of quantifying how much time trajectories avoid certain subspaces, especially some closed orbits or ambient spaces. And it has a long history, and it goes all the way back to Margulis in 1971 when he proved the non-divergence of unipotent flows, and then came Danny's paper in 79, quantitative version of non-divergence, which led to the celebrated theorem of Ratner in 90 and 91. So that's where everything started. And today I'm going to talk a little about not the unipotent flow, but the expanding translates of them by the diagonal flow. And yes, so moving on to the setup. The setup in general, for our main theorem, the setup is quite general. So our group G will be semisimple algebraic Lie group without compact factor. And we have a lattice gamma. It need not be uniform, so it can be a non-uniform lattice. And our space X will be G mod gamma. And we have H, and we'll think about H orbits on space X. And what is our H? H is a semisimple subgroup of G, again, without compact factors. And moreover, the centralizer of H is finite. Why do we need this condition? Is essentially because we want to have only finitely many subgroups in between G and H. And for each of those subgroups, which we will later denote as S, we want to say something like certain trajectory avoids all S orbits of bounded falling. So that's what's it gonna be. And we have a one parameter diagonal subgroup AT within H, and U is the unstable Horo spherical subgroup in G with respect to the flow AT. So it's quite abstract, but the example case that you might want to keep in mind is G is simply SL2C, gamma is SL2Z extension by I. So in this case, gamma is uniform, but okay, we'll talk about non-uniform cases only in last 10 minutes. So this would be happy enough. And our H subgroup is SL2R. Note that there is no subgroup in between SL2C and SL2R. And the diagonal flow is the usual e to the t over 2, e to the minus t over 2. And U is the unipotent 1z. Okay,
so this example is indeed non-uniform, right?
Oh.
Yeah, I was.
Oh, sorry. Yeah. This is non-uniform. Sorry. Yeah. Yeah. Maybe we need a more complicated gamma to be uniform.
But you want it
to be
uniform, or you don't care?
For the most of my talk, I'll first focus on the uniform case, and then in the last 10 minutes, like how I'll give a brief sketch on how it should be altered in the case of non-uniform lattices. Okay. So yeah. But thank you. And okay, sorry. So talk about the quantitative non-divergence in to talk about avoiding principle in quantitative language, we need to define some quantitative version of Diophantine condition. So we say that an element x in X is VD Diophantine if it avoids all closed S orbits where S is a subgroup in between H and G. And we consider all of these orbits that have a volume less than V. So that is our first parameter V. And for all this closed orbit, our point X is at least apart from those orbits by distance D. So that is our definition of VD Diophantine condition. And as I mentioned before, in the case of SL2C and SL2R, there is no subgroup in between. So you can simply think about this as considering all the SL2R orbits of small volume. Oh, sorry. And so here's our main theorem. It's titled as avoidance principle. So there are some absolute constants D, A, and C, where D only depends on the dimension of G, not on gamma and not on H. And A and C are constants that depends on G, gamma, and H. Then what is our result? It's that dichotomy, the following dichotomy holds. For any point X in X, there exist T's of X such that for any pair large capital T and capital R, either X is not R1 over T Diophantine. This means that there is a closed S orbit that has a volume smaller than R and is close to X by 1 over T. Or if that's not the case, which means that if X is R1 over T Diophantine, then if we wait for small t, so this is the time parameter. So if we wait long enough, depending on this large T, then what we have is this ATs of use of X, where U is in the unit ball of the orthospherical subgroup U. This ATs of use of X will first lie within the compact part of the space X. So the injective radius has some lower bound. And second, this point has the improved Diophantine condition by R and R to the minus D. And we're saying that this this happens in the majority of case, and the measure is given as 1 minus some absolute constant C times R to the minus 1. So this is our result. And what is really good about it is, suppose that X is not on closed S orbit of small volume, then it will have some, however weak it is, it will have some version of Diophantine property. So let epsilon be the minimal distance between X and small volume S orbits, then we can just set it as 1 over T. Then, okay, the time variant depends on this value of T. So if X was initially very close to certain S orbit, we might have to wait longer, but in the end, at the end, what we have is that these points, ATs of use of X, expanded translates of unipotent orbits, these points have Diophantine property not depending on the initial Diophantine property of X, but only dependent on this R, which is the volume vector. So that's what our main theorem is saying. Okay. And moving on. So in the journey of proving theorem 1, we have 2 more seemingly useful theorems that show up. First thing is quantitative isolation of closed orbits. So it's saying that given any two closed s orbits, y and z, the distance between y and z within the compact part of X can be uniformly bounded in terms of volume of y and volume of z. And this power that we have is again a global absolute constant that only depends on dimension of G. And the next theorem, which directly follows from theorem 2, is that we can give an upper bound for the number of closed orbits of bounded volume. So the volume, so number of closed s orbits of volume less than r is bounded by some power of r, where the power d is again some absolute global constant. So relating this to the previous works, as for this avoidance principle, there is a result. There is a result in 2019 by LMMS. So it's it's again a quantitative avoidance principle for unipotent flows, but our version is for expanding translates of it. And as for theorem number 2, there is in some sense more general version by Eskin, Margulis, and Venkatesh, but we would like to argue that our version has somewhat softer proof, because the proof in EMV 2009 used the uniform spectral gap for periodic orbits, and so their assumption was that gamma is arithmetic, but we don't need the arithmeticity condition, and the only tool that we use is Margulis function. And
so EMV is probably Einsiedler plus.
Oh, sorry, yeah.
That's right.
Sorry, yes, Einsiedler. And yes, and theorem 3, there is a similar analogous argument in Mohammadi 2020, and it's for the infinite volume 3 manifolds. And so the main idea there was how to deal with the infinite volume when gamma is some discrete subset, not necessarily lattice. But here we have more general setting for G, but our gamma is a lattice. And actually the idea of using Margulis function to give a quantitative version of isolation of orbits that goes all the way back to the unpublished notes by Margulis. And he proved for the case when gamma is uniform, but here we're combining that result with height functions, and we're proving for the case when gamma is non-uniform also. Yeah. Thank you. And yes, so going into the main ingredients of the proof. So obviously Margulis function is the most important technique, and there are linear algebra lemma and height functions, and we'll discuss them later onwards. So maybe some footnotes on Margulis theorem. It was first introduced in 1998, Eskin Margulis Moses paper, where they proved quantitative open-IM conjecture. And it turned out to be a powerful tool in studying settings where there is no nilpotent dynamics at all, or when the nilpotent dynamics exist but is kind of poorly understood. Since Margulis functions, it's a class of functions that satisfy 2 axiomatic conditions. We have quite a few room to set up our own Margulis function, so it's kind of there is some room for universal application. So, for example, there is a result by Benoit Kahn on stationary measures, which was further generalized by Eskin-Lindenstrauss. And there are various applications of it in tachymeter dynamics, Eskin-Mesur 2001, Athrea 2006, and also in space of lattices, Kadanoff, Kleinbach, Lindenstrauss, Margulis 2017, Kleinbach, Mizede 2020, and also for like finite and infinite volume homogeneous spaces. I've already mentioned Mohammadi 2020, and there is also Rodriguez, Hertz, Wang 2021 paper, and there are so many others, but maybe I'll stop here. Sorry if I didn't mention some relevant names, but yes, I'd like to move on to the definition of Margulis functions. So Margulis function f is defined on x, this is G-mod gamma, going to the positive reals. And we have only two conditions, two abstract conditions. The first thing, we need log continuity. So for any compact set K in X, there exists constant sigma, which depends on K, such that for any X in X and G in K, if we alter X by G, then the value of our Margulis function only goes up or goes down by sigma. So that is our log continuity condition. And second is the important Margulis inequality. So it is saying that for some C in between 0 and 1, and some time t, which is dependent on t, some large time t, such that the average of the Margulis function over the expanded translate of unipotent flows, so U varies over the two-ball and horospherical subgroup, and you expand it by a sub t, then this average will diminish by the factor of c, and possibly we have an additive constant b. So that's our Margulis inequality. Now, why is this useful?
So is a
oh, sorry. Yes.
Is a constant function a Margulis function?
Yes, constant function is a Margulis function because you can just set c to be 0 and b to be that constant. Then this if f is a constant function, namely f equals d, then just let small c to be 0 and b to be d. Right. Then yeah, okay. It's a stupid Margulis function, but it's still a Margulis function. Yeah, thank you. And why is this useful? Because if we have this Margulis inequality, we can actually move along by this TC. And if we go by NTC, then we have exponential decay by C to the N with whatever some absolute constant C upon it. So, and of course, we need a continuous version where this is NTC is a discrete version. But so to give a very brief sketch of how this exponential decay happens, let's just think about a sub 2t. How it goes is, okay, if we apply a sub t to both sides of this Margulis inequality, then we would have a sub tf is smaller than a sub t cf plus b. So this atf expands into cf plus b. So we have c to the squared factor, and we have some constant over here. Later, it will be something like small b times 1 plus c squared, and so on. So this is bounded above by 2b, so you don't have to worry about it. The thing that is in concern is how you can approximate this two-step random walk AT sub f by one-step random walk A sub 2 TF. So this is, we're choosing two different elements in the or spherical subgroup. So it's AT sub U1, AT sub U2, and then X. Whereas this guy, we're choosing only one unipotent element, and then we're expanding it by 2T. But it isn't a serious matter, and it can be well approximated up to some absolute constant, which was the large C over here. It's simply because if you conjugate this U1 into U1 prime, so we're saying that U1 AT is AT sub U1 prime, then this U1 prime will be contraction of U1 in size by e to the minus t. So if you think about the density function that appears where this U1 prime varies over b to the e to the minus t, and U2 is in b to the 2, it's up to constant, can be approximated the uniform measure on the unit ball on B1. So that's what's happening here. So we have an exponential decay, and then what is good about exponential decay is that letting our t to be large enough, we can let our c to the n, this factor, to kill f. So no matter what our initial value of Margulis function fx was, if we wait time t long enough so that n gets large enough, then we have that this part gets majorized by this factor b. So AT sub f will be bounded by b. And then we'd like to introduce the Margulis function that we actually use, and assuming that this function that I introduced is a Margulis function, so we'll not assume that this satisfies Margulis inequality and directly show how the proof of our main theorem appears. So yeah, actually here I wrote Margulis function of our choice, but this is more or less the standard choice that everyone takes, and it goes back to EMM. So yeah, I should be honest about that. So first we fix a single s orbit. Since we know there are only finitely many subgroup S in between H and G, and our theorem 3 says that for each S, the number of closed S orbit of bounded volume is finite. Later, combining all those different orbit is easy. So essentially, all we have to do is show for a single closed S orbit of bounded volume. And what our Margulis function will be as follows. So basically, the idea is what we really want to track is, given a point X, we want to look at the closed S orbit that is closest to our given point X, right? But if we only consider this closest S orbit, if we flow along by AT sub u, there is no guarantee that for the point AT sub u sub x, this orbit will remain, this sheet will remain as the closest sheet, right? So what we're trying to do is, as shown in the figure below, we think about the window around X, and we take account of all the sheets of closed S orbits, sheets of this SY that is close enough to this X that comes within this window. So how is our window set? Basically, it has to come within the injectivity radius of X, because there's where we can do honest action by G. So this window is within the ball of radius injective, within the injective radius of X. And then what's good about it is we decompose our G. It's Lie algebra. Lie algebra of G, we decompose into Lie algebra of S and direct summand of Vs. Then for any point y that is in the window, which is ball in G and injectivity radius of X, and then centered X, y can be written in a unique way where we have X of V1 and X of V2 of X, where this V1 belongs to Lies of S, and this belongs to Vs. So that's how we divide the chart. And note that since S orbit is clearly S invariant, the sheets will fully cover the window as shown in the figure, and we set these small vi's to be the distances that we have. So if we have X and we go by X of V, then it lies within this closed orbit. So these VIs are really measuring the distance between a few nearest sheets of Y, and we let IY to be the set of all those vectors V in Vs. And our Margulis function Fy is defined to be the energy function defined over the set Iy. So we take minus alpha to the size of these vectors V in the Lie algebra, and we take the summation of it. So this is, in some sense, the energy function. And in extreme case, if nothing comes within this injectivity radius window, then we'll just be stupid and say that it's injectivity radius to the minus alpha. So for times being, let's just consider our gamma to be uniform lattice. Then what's good about it is then X will be compact, and this injectivity radius will have a global lower bound. So this is nothing more than an honest constant, some large honest constant. But in non-uniform case, this also varies, and this might also diverge. So there are some technical difficulties which we have to fix by height functions, but we'll talk about that later. And yes, so we move on. Now, assume that this energy function we've just defined is indeed an honest Margulis function, which means it satisfies log continuity as Margulis inequality. Then the theorem our main theorem directly follows essentially by Chebyshev inequality. How does that go? Is that we've seen that from corollary that if we pass by time t long enough, then the average over the expanded translate will be smaller than some absolute constant b, right? So it is the average of this Fy AT sub u is bounded by b. So by Chebyshev inequality, the points u such that the value of Fy is greater than b squared must be smaller than b to the minus 1. And how does this directly gives the proof is because this Fy already involves the smallest vector. So if the smallest vector was very, very small, that would eventually make Fy sub x very, very large. So this set that we have is x is r comma b to the 2 alpha Diophantine. X is not, sorry. This set is a subset of this guy, so that eventually leads to the proof, because this Fy is smaller than, greater than v to the alpha over 1, where this v is the measurement of the distance between x and the closest s orbit of small volume. So that's how the game ends. And since there are some mysterious constants that I haven't clarified, we need to clarify what our b is, and we have to say more about what this time t will be. So I'll give more explanations on that. So going back to this exponential decay statement, why were we able to do this was we were killing this f by c sub n, right? So if the value of fx was large, then we would have to wait longer in time t. So that's exactly what happens here. So the time that we have to wait depends on the initial value of this Margulis function at point x. So this fyx is essentially a parameter that is very closely related to the Diophantine property of x. So to recall, our main theorem 1 was saying that if x was r1 over t Diophantine, if you wait long enough, we would have r comma r minus d Diophantine. So this 1 over t is closely related. So that's how the condition that t is greater than a logs of t is given. So going back to our main theorem, that's where this condition that small t is greater than a logs of t comes in.
So I'm a bit confused. So you have the main theorem, but
sure, yes.
You said that in order to prove the main theorem, you're proving first the other theorems. So how does the logic go? You start by proving which theorem comes first?
Theorem 2 comes first, theorem 3 is next, and then we prove theorem 1. So theorem 2 and 3 appears necessarily in the proof of theorem 1, but we thought that theorem 2 and 3 are somewhat notable in its own,
But Margulis
sense.
functions are used to get from theorems 2 and 3 to theorem 1. So the
Margulis functions are used multiple times.
That you're using.
So essentially what we need is theorem 3, because later what we're saying is that, okay, if you're talking in a single orbit sense, you don't need theorem 2 or theorem 3. But to combine all, to say that it avoids all s orbits of small volume, you first have to claim that the number of closed s orbits of small volume is finite. And that's from theorem 3. And theorem 3 is also proved by using Margulis function, but in somewhat different way. Okay, thank you. So yeah, so this was the general overview of our proof for theorem 1. And something that we haven't explained is, okay, where did this mysterious constant B appeared? So this B was essentially small b times 1 plus c plus blah, blah, blah. So this large B was essentially 2B, but with this constant C, which appeared from this adjusting density. So this B is some absolute constant times small b, where small b comes from one-step Margulis inequality. And later we will show that this B for our Fy appears in terms of volume of Y. So large B comes in a function of small b, and small b for this single orbit Fy can be interpreted in terms of volume of Y. So that's where all the figures join in and make the constants that appeared in our theorem 1. And this volume Y was dependence on R and had nothing to do with T. Yes, so I guess the most important step is to actually show that why this energy function that we've defined actually satisfies the Margulis inequality. So I'm going to do that. So first we have point X, and we have a window around point X, and we flow by AT sub u, and we have a new AT sub u X and new window of size injectivity radius of this point and a new window. So our claim is that the sheets that were close to this point can be tracked back to the sheets that appeared here. So for some epsilon over here, if it was within the epsilon bound within this window, then these guys should have originated from the window in X. So that's what we're going to say. And then how do you consider the things that were outside? We don't have to worry about them too much, because these outside black sheets have a lower bound for the size of this vector v, which is distance, which is epsilon. And all we have to worry about is, okay, how many of these black sheets exist? And that will be given in terms of volume of Y. So that's our strategy. So to write down, for convenience of notation from here on, we'll just say H equals AT sub u. So f of y hx is summation of vectors, summation of energies of vectors v in the window around hx. So first we'll consider the uniform. Oh, sorry.
What is
yes.
I missed this part. So what is alpha? Alpha is completely arbitrary. Can be anything.
Oh, alpha will be later determined as so that it satisfies linear algebra lemma, but it's
okay. So
it has some conditions, but it doesn't matter in the proof. It doesn't matter in the proof in this stage. Yeah, it's just considered as some whatever constant.
Okay.
Yes. And yes, so the key point here is this v in iy of hx, exponential v applied to hx is in y. So that's it. And since, so here's the idea, since y is s orbit, it's clearly s invariant. And since s is a subgroup in between g and h, y is clearly h invariant. So we can put another h inverse over here and say that h inverse of this guy is still within y. And so exponential of adjoint action of H inverse to V applied to X is within Y. So we started with HX, but we ended up something similar with X. So all we need to check is if V has a small size, then this adjoint H inverse to V also has a small size. So this guy belongs to IY sub X. So this guy is something that contributes to F of Y. That's how it goes. And so for this H, we're going to say that we know that there exists some absolute constant C, such that for any vector V in Vs, so Vs was the direct summand of least of S within least of G. So any V in Vs, whenever you apply the adjoint action by H inverse, you can at most grow by C, at most decrease by 1 over C. So there exists such constant C. Then this F of Y, we split into two guys, red sheets and black sheets. So if it belonged to red sheets where V has a small volume, then those guys can be tracked into elements in I sub Y sub X. And since this, since this V in I sub Y sub HX and V smaller than epsilon over C, where the C is this constant over here, and epsilon, I'm just saying this to be the global lower bound for injectivity radius. So we're thinking in the uniform case first. So if this happens, then adjoint H inverse of V is in I sub Y sub X. So this V is adjoint H times W for some W within I sub Y sub X. But there may be some other sheets within I sub Y sub X also. So this gives an inequality. And then for the later part, we have an lower bound for the size of V. So we simply substitute. So it's epsilon over C times minus alpha, and then simply whatever number of sheets that happens. Number of sheets within the window of HX. So that's our inequality. And moving on. So first, we're going to say that this number of sheets is exactly bounded by volume of Y. How does it go? The volume of Y is, of course, greater than or equal to the volume of sheets that appear within the window, right? So and how do you measure the volume of these sheets? Each and every of these sheets has size of e to the dimension of s. Since we are writing on a board, it seems like a two-dimensional space, but recall that this direction was Lie algebra Vs, and this was Lie sub s. So this sheet is actually of dimension of Lie sub s. So, and this width is injectivity radius of x, which we will say is epsilon. So this is epsilon to the dimension of s. So this is some global constant. And so this times this is smaller than this. So this guy is, the number of sheets is bounded by volume of Y times some absolute global constant. That's what's happening. And this part, how do we deal with it? It's measuring for each element H, for each independent H, which H was ace of t times u, we cannot say for sure whether this guy is comparably small with respect to f of y of x, which is this guy. So we cannot fix one H and compare these two. But if we take average over all H, so we're taking average over all U and B1s of U, then we can say something. Then it says, okay, we have the sigma over all W's, whatever, and we have an average of ATs of U acted to W, where the average is B1s of U, and this is the M's of U. MU is the Haar measure on U. Oh, sorry. And what we want is we want to compare this average with omega 2 minus alpha. So this is what we call a linear algebra lemma. So the statement is, for any W in Vs, which was a subset of Lees of G, for any W, if you average this over the expanding translate of unipotent flows, then this guy will exponentially decrease. And where does this follow is, okay, give me any vector W in Vs. So this is vector in the Lie algebra. Then this guy will have expanding direction in terms of AT and stable and decreasing direction. And what this U is doing is, for majority of U, this U will put our W in general position. And what I mean by general position is that this UW have non-small component in the expanding direction with respect to ace of t. So maybe I should write down here. So if we have W, and this W can be decomposed into two vectors, W1 and W2, this guy will exponentially increase when applied by ace of t. This guy will either remain stable or this guy will exponentially decay, but we don't care about it. And what we only care about it is this omega-1 has size that is not small compared to the original size of W. Maybe you cannot guarantee if you choose an arbitrary element W in Vs, but here this U does that for us. So we're averaging over U, and this UW is put into general position, and so this UW1 is non-small, and these guys exponentially grows, so this entire thing exponentially decays, and we have something like that. And here we have some restriction on alpha according to the Lie algebra structure of G, and there's where the restriction in alpha is given. Yeah, maybe I should say some credits. So this kind of decomposing and this general position kind of argument goes back to the paper of Nimish-Shah in 1996. So he proved that for most of u sub w, the size of, there is a global constant c such that u sub w sub 1, so this is the expanding direction. So this norm is not so small compared to u sub w. And for this specific linear algebra lemma, we're adopting the version written by Katz in 2020. Okay. So yeah, that was the general outline, and now we know how the Margulis inequality is proved. And more important thing is we now know why this additive constant is appears in terms of volume of y. So that's most of the SketchUp proof. And I think I'll just spend only 5 more minutes on describing how it should be modified when the lattice gamma is non-uniform. So we kind of cheated that this injectivity radius has a lower bound. In that case, this is a constant, so you don't have to worry about it. But when this does not have a lower bound, we have something non-trivial in mind. Suppose that fy of x appears to be injectivity radius of x, and all f of y ATs of ux also appears to be injectivity radius of ATUX to minus alpha. Then we would need some kind of argument that this injectivity radius to minus alpha power is itself a Margulis function. We need that in order to show that this guy is a Margulis function, right? Fy is a Margulis function. But actually proving that directly for injectivity radius is not so easy, and there is something already introduced. So the primitive version is already in Eski Margulis Moses paper in 1998. They used something called alpha functions, which is a primitive height function for SLNR mod SLNZ, and it was later developed to the general semisimple Lie group case. And there exists a height function h that is comparable to up to some global constant. Hx is comparable to some mth power of injectivity radius of x, and this h itself satisfies Margulis inequality. So instead of using injectivity radius of x to minus alpha, we need to put h of x over here, h of x to some minus kappa power over here, and the definition of I sub y x should be also in terms of some eta, some small eta times some hx to m, where this m is this m over here. So that should be the modification. And I'll just end my talk with explicitly showing what height function is in the case of SL2R mod SLNR mod SLNZ. So yeah, when G is SLNR and gamma is SLNZ, it's the space of lattices. It's essentially the spaces of lattices. And so we define alpha I to be the inverse of smallest co-volume that can happen on dimension I. So L subspace L in Rn is called delta rational if L intersection delta is a lattice in L. And for each I from 0 to n, we define alpha I to be the inverse of smallest co-volume, and alpha sub delta, which is the height function, is simply the maximum of alpha I sub delta, where I ranges from 0 to n. Yes, I think that's all I wanted to say today. Thank you.
All right, let's try to get some round of applause. We can hear and see. Any questions? Juno? So I'm a bit have a question about the very last thing. So your what is the statement here? You have this alpha i's and alphas, but then how do you get h?
Oh, so this is our h.
Function.
So yeah, this is our height function. So this indeed
alpha is the height
yes,
function, just the maximum.
Yes, alpha is the height function, the maximum of all alpha i's.
In the asking Margulis Moses construction, there was some choice of weights, which I think happened to be important.
Oh, yes, we can put weights.
Well, if you don't have to, you don't need to. So you're saying
the weight kind of effectivizes inequality bounds, but even without putting weights to each of alpha I, the Margulis inequality still holds. Does that make sense?
But and you're saying it's comparable to injectivity radius? I thought injectivity radius is.
Oh yes, that's important. But like adding some constants here does not change. Only changes the constant, absolute constant that appears here, right? It doesn't change the degree. So the weight does not matter.
Sure. Okay, maybe. I thought injectivity radius is connected to alpha 1.
Yes, right.
Not the case. Okay, anyway. So,
yeah. Yes, but that's why we have degree m over here. Alpha 1 is directly h. And if alphas of I, the other I rather than alpha 1 comes into the position, then we need to consider this degree m.
So the degree is changing?
Oh, sorry, yes. Maybe, yeah, I might have to write it in the other way. Injectivity radius to m1 power, and then
okay, yeah,
h of x. Yeah,
this I believe.
Yeah, this is the honest argument. Sorry, yeah.
Okay.
X to the m2. Yeah.
Okay, that's more plausible, I guess. Okay, other questions? Comments?
Thank you for a very interesting talk.
Oh, thank you.
Yes, I agree. So, so now that we hear Jadev, what is the implication of all this for Teichmüller dynamics?
So
Jadev has his own Margulis functions on those spaces given by saddle connections. Does it ring any bells? Yeah.
Oh, so the question is for me? Or
of course, you're the speaker.
Oh, well, to be honest, like I know that these kind of Margulis function technique also appears in Teichmüller dynamics, but I haven't studied that a lot. I know that Etheria has a paper in 2006 and some more, but I haven't, to be honest, I haven't read those papers thoroughly. So maybe
that's a question to Jadev.
Yeah, I can make a couple of remarks here. So one is that Yeah, so the functions that I used in that 2006 paper are basically built in Eskin and Mazur's work, which was inspired by Eskin, Margulis, Moses, right? So they build similar alpha functions with lengths of saddle connections and what are called lengths of complexes, and you put them together in a similar way. And I got recurrence results for visiting for coming back from infinity. But similar ideas were actually used. This talk reminds me a lot of in the Eskin, Mirzakhani, Rafi work. They need to stay away, and Eskin, Mirzakhani, Mohammadi, you also need to stay away from other orbit closures. And so they have functions that measure how close you are to other orbit closures instead of just the cusp. So this has a lot, this Margulis function set of ideas has a lot of uses in Teichmuller space. I don't know that work, the details as well, but again, essentially you have functions that measure how close you are to other orbit closures. And then you can say, oh, I stay away from it. Most orbits stay away from these other orbit closures. So spiritually, it feels quite similar.
Okay, thank you. Questions?
Thank you.